proportional to C2 as a function of time modulus squared. And this C2 as a function of time was given by minus iota h bar integral from 0 to t e minus I omega fi t dash, and the matrix element for the perturbative Hamiltonian that connects the initial state with the final state. Okay. So this is the coefficient to first order, which determines the probability amplitude for this state as a function of time. And when we take the modulus squared of this, we will get the probability that at time t, you started off with only this state being populated. At time t, the probability that this state is going to be populated is given by this. And this formula is only valid when these probabilities are much smaller than 1. Okay, so this is only then will the first order approximation be valid. And then we look at several examples. This perturbative Hamiltonian in general will have a time dependent one. So one example that we were particularly interested in is that if we have this two-level system and there is light coming in at a certain frequency h bar omega, we start off in this state. What's the probability that this state will be populated? So the perturbative part of the Hamiltonian hp was given by some coefficient v, say sine omega t, where omega is the frequency of the incoming light, and we also define omega naught, which is the characteristic of the system given by the difference in energy of these levels. Okay. So for such a case, which we call sinusoidal perturbation case, we also found out that the probability as a function of time of going from 1 to 2 is approximately given by V modulus squared over 4h bar squared t squared sin squared omega minus omega naught t by 2. Right? ये हमने पिछले किसी लेक्चर में डिराइव किया था. Whereas this V, this term V, is in fact a probability amplitude. This probability amplitude is the inner product that connects the initial with the final state. So this V is just a shorthand notation of this matrix element. Okay. अच्छा, ये भी formula उसी वक्त valid है जब the probabilities are really small. And notice that we're talking here about the difference between the applied frequency and the resonant frequency of the system. And this formula is only valid when omega is close to omega naught. That is, we are at the near resonance or perfectly on resonance conditions. And if you make a plot of this probability versus time, and instead of, okay, you can notice that this probability is a function of time and it's also a function of omega. So you can put in a parameter omega here as well. So we can plot this probability at different times as a function of omega. So this can be our frequency axis. This is our probability axis, p omega. Now t is a parameter. ठीक है ना? हम इस probability को देख सकते हैं कि incoming light की frequency omega है. तो different times पे probability क्या है? अगर system इस state में शुरू हो रहा है, तो we can make these plots. So this plot will have a maximum at a certain value of omega, which is omega naught. Okay, यहाँ पे इसकी p को भी एक sinc function है, sinc squared function है. The probabilities are always positive, so this is the kind of function that we will take. ठीक है? इसकी peak है omega equal to omega naught. तो maximum probability उसी वक्त होगी जब perfect on resonance को state. ये probability याद है, ये formula valid उसी वक्त है जब time छोटा है. ठीक है? इस function को देखें अगर आप, इसकी आप maximum probability निकाल सकते हैं. और दूसरी बात ये देख सकते हैं कि ये जो side lobes हैं बहुत छोटे हैं, इनके अंदर जो area है वो बहुत छोटा है. So most of the excitation is taking place here. ये एक्साइटेशन का प्रोसेस ही है ना कि ग्राउंड स्टेट में आप शुरू कर रहे हैं, आप लाइट फेंक रहे हैं, आप पर्टिकुलर फ्रीक्वेंसी का एक्साइट हो। और ये भी याद रहे कि लाइट यहाँ पे कंटीन्यूअस वेव के तौर पे ट्रीट हो रही है, ओमेगा। लाइट इज नॉट बीइंग ट्रीटेड एज अ हार्मोनिक ऑसिलेटर, कंटीन्यूअस क्लासिकल फील्ड। अच्छा, ये जो पॉइंट है ये पॉइंट होगा ओमेगा नॉट प्लस 2 पाई ओवर टी स्मॉल टी, और ये पॉइंट होगा ओमेगा नॉट माइनस 2 पाई ओवर टी। ठीक है, इसका मतलब ये है कि if the time of observation is small, if the time of observation is small, this 2 pi over t is large, so this lobe is bigger. So if you observe the probabilities over a small observation time scale, more and higher, a bigger spread of frequencies will be able to excite the system from the ground to the excited state. If you observe long enough, if t is really large, if t is large, this central lobe is small, which means that only you can excite only at or near the resonance conditions. The probabilities elsewhere will be 0.
So what does that physically mean?
Okay. By the way, you cannot make t arbitrarily large, because this formula is only valid for small probabilities. Because if you make t's really large, then you notice there's a t square factor here as well. So this probabilities keep on increasing as t increases. Okay. So what this really means is that if you would like to excite a system on resonance, okay, then you really need to wait for a long time. This is just the uncertainty principle at work. If you apply a bigger spread of frequencies, that is, your incoming radiation has a bigger spread of frequencies, then it's possible to a bigger spread of frequencies means that this lobe is bigger, but you can observe such an effect only when the time of observation is small. This means you can apply a pulse that is extremely small in the temporal scale, like a femtosecond laser pulse, or if you apply such a pulse which is small in time, then you can excite over a bigger frequency range, which has a bigger set away from the resonant condition. If you apply a truly monochromatic laser which has a small frequency, right? It has a small. This is small. Then it would take extremely long for you to see excitation. Okay, but then the problem is that this formula only holds true when this time is not too big. Okay, because that's a limitation that comes out from the perturbation theory. ठीक है. अच्छा, अब हम थोड़ा सा इसमें आगे चलते हैं. अब हम ये करते हैं कि
you said कि if we apply a large spectrum of frequencies तो फिर जल्दी से हो जाएगी resonance.
जल्दी से रेजोनेंस नहीं होगी. रेजोनेंस अगर हम बिगर स्पेक्ट्रम पल्स अप्लाई करें, ठीक है, बिगर स्पेक्ट्रम पल्स उसी एक्साइटेशन उसी वक्त होगी व्हेन दैट बिगर स्पेक्ट्रम पल्स इज ऑफ अ नैरो टाइम ड्यूरेशन.
So if we shorten the time duration, we can achieve transitions even with larger differences in frequency.
Exactly. अच्छा, अब दूसरा अगर हम देखें कि अगर हम एक एटम है उसको किसी फील्ड के अंदर रख देते हैं, एटम इन अ फील्ड, तब ये सिचुएशन किस तरह तब्दील हो रही है. सपोज द सिस्टम दैट वी टॉकिंग अबाउट नाउ इज एन एटम एंड वी टॉकिंग अबाउट इलेक्ट्रॉन्स दैट आर एक्साइटिंग और de-exciting inside an atom. So what is happening here is that we have to identify a perturbative Hamiltonian, Hp. Okay. This Hamiltonian clearly is the dot product of the electric dipole moment with the applied electric field. Okay. This is also an operator. ठीक है. ये तो हम कई दफा देख चुके हैं. म्यू को आमतौर पे d से भी जाहिर कर सकते हैं. ठीक है. So the electric dipole operator dot product with the electric field. Suppose the applied electric field is time dependent. ठीक है. That's what electromagnetic radiation really is. ये बात समझ आई है आपको? यहाँ पे देखो, इस बात को दोबारा हम एक दफा यूं देख लेते हैं कि ये है आपका एक्साइटेशन कर्व. ठीक है. अगर टाइम इज स्मॉल, if you observe the probabilities over a smaller time scale, then this thing is going to be small, this thing is going to be large. What you will observe is a curve like this. Okay. So this means that the excitation is possible over a larger frequency range. You apply an incoming radiation that is further away from the resonant frequency, still there is a bigger probability that the system can be excited. A bigger probability of finding the electron in the excited state. That's what it means. Okay. Even for shorter time scales, you observe the system for a shorter time scale, and it's possible that an incoming radiation that has a frequency far away from the resonant frequency can still excite it. ठीक है, ये अनसर्टेनिटी प्रिंसिपल है और कुछ नहीं। अच्छा, अब यहाँ पे अगर आप देखें एटम को अगर आप फील्ड में रखें, transitions are possible. Such a transition is called an electric dipole transition, because here we talk about electric dipole. What happens is that the electric dipole interacts with the applied electric field. Suppose this applied electric field is time dependent. It's sinusoidal. Suppose it's cosine omega t with some E naught. ठीक है, मैं E naught को थोड़ा सा इलेक्ट्रिक फील्ड को जरा इस तरह की E से सेलेक्ट करूँ, सिरिलिक E से, कैपिटल E से मैं एनर्जी को सेलेक्ट करूँगा, ठीक है। और जाहिर है किसी न किसी डायरेक्शन में होगी, लाइट पोलराइज्ड हो सकता है। Suppose it's polarized along the z direction. So in such a case, the perturbative Hamiltonian becomes minus dz E naught cosine omega t. Correct? Now this is also a sinusoidal perturbation. ठीक है, ये भी एक sinusoidal perturbation है। यही फॉर्मूला यहाँ पर यूज करेंगे। So if I write down the probability of making a transition from 1 to t when my initial state is in the ground state, I will get I need to put in a transition matrix element. Now this is just a scalar E naught. So this dz modulus square, right? ये ट्रांजिशन मैट्रिक्स एलिमेंट शॉर्ट हैंड नोटेशन में लिखा है, ठीक है। मैं भी बता दूं इसका मतलब क्या, E मॉडुलस स्क्वायर्ड, राइट। ये आपका टोटल V मॉडुलस स्क्वायर्ड है। देन वी हैव अ T स्क्वायर टर्म, देन वी हैव 4h बार स्क्वायर्ड, देन द सिंक फंक्शन, सिंक स्क्वायर्स ओमेगा minus omega naught E by 2, right? So this is what happens when you place an electric dipole, aka an atom inside the classical electromagnetic field. Now this dz that we have here, this dz, what's this dz? This dz is simply a shorthand way of writing dz in a product. Initial state is ket 1, final state is ket 2. एक मैट्रिक्स एलिमेंट है इलेक्ट्रिक डाइपोल ऑपरेटर का, और dz क्या है? dz is minus E bra to z, right? So this is what the electric dipole operator is. It's minus the charge times the position operator. ठीक है, तो आपके पास अगर इनिशियल स्टेट हो कोई और फाइनल स्टेट हो कोई, तो आप उससे ये प्रोबेबिलिटी निकाल सकते हैं। मिसाल के तौर पे, your system starts off in the state in the 1s orbital. You have a hydrogen atom starts off in the 1s state, so you have n equals 1, l equals 0, mn equals 0, ठीक है। और आप ये इस हाइड्रोजन एटम के ऊपर इलेक्ट्रोमैग्नेटिक रेडिएशन, ठीक है, of a particular frequency omega, ठीक है, and you would like to find the probability of making a transition to the next excited state, say any state. So you're going from 1, 0, 0 to n, l, mn. Okay. So the probability of making this transition as a function of time will be E mod square, the modulus square of this, n, l, m, l, z की जगह ये z ऑपरेटर और 1, 0, 0 मॉडुलस स्क्वायर, राइट। और साथ दीगर टर्म्स है t स्क्वायर, 4h बार स्क्वायर, सिंक स्क्वायर, ओमेगा माइनस ओमेगा नॉट, ठीक है। दिस इज द प्रोबेबिलिटी ऑफ मेकिंग द ट्रांजिशन। नाउ we have to calculate this term. Okay. Now if you look at ML 0 1 0 0, let's look at this inner product. It's a complex number. ठीक है, इसको सिर्फ इस कॉम्प्लेक्स नंबर को देखते हैं, इसका बाद में हमने मॉड्यूलो स्क्वायर लेना है. ठीक है, ये z दरअसल, now this is proportional to something. Let's write this in spherical coordinates. For this z we have cosine theta, right? R cosine theta. ठीक है, मैं अभी रेडियल पार्ट में लिख रहा हूँ, सिर्फ उसके एंगुलर मोमेंटम वाला पार्ट. ठीक है. Now what is this? This is a spherical harmonic function. This is y 0 0. What's this? This is also a spherical harmonic function. Y L M L complex conjugate, right? ठीक है, अब मैंने ये इनर प्रोडक्ट लेना है, इसका मतलब I have to integrate over the volume. So I have a sin theta. I integrate over sin theta, d theta, d phi. ठीक है, theta and phi. सही है ना? Okay. Now remember, this is just a scalar 1 over 4 by under root टेबल मैंने आपको दिया हुआ. This has no angular dependence. It's just the s orbital. ठीक है, इसकी कोई angular dependence. अब हमने parity देखी different functions की. ठीक है, तो एक बात रह गई, sin theta cosine theta is an odd function. Sin theta cosine theta is sin 2 theta. So this is odd. This has odd parity. Okay. And if you look at this function has the parity equal to L. Okay. So this means that this integral will only be non-zero when L is even. If L is even, then the product of this even with odd will give us 0. If this L is,
So minus 1 will
also okay, minus 1 is for L. If L is even, then this function is odd. Okay, in L even, then the YL-ML complex conjugate is odd, and it multiplies with the odd sin 2 theta function to give you an even function. Okay, so then the integral will not vanish. If L itself is odd, then this function is even, the y function is even. It will multiply with this odd function to give you an overall odd function, the integral will be 0. This means that this inner product is non-zero only when L is even. Only when L is even. Oh, sorry, I'm making a mistake here. I'm sorry, I'm making a mistake here. I don't have, okay, what do I have here? I have sine, I'm taking the integral, sine theta is my measure, the volume measure. I have, this is just a scalar. This is just 1 over 4 by under root. Okay, I have this function y L M L complex conjugate, and I have cosine theta. Now what is cosine theta? Cosine theta is proportional to y 1 0. ठीक है, it's the z orbital. ठीक है ना, क्योंकि y 1 0 is proportional to cosine theta. y 1 plus minus 1 is proportional to minus plus sine theta. E plus minus I phi, right? Okay, so this cosine theta is just the z orbital. It's proportional to the z orbital, right? It's the spherical harmonic function will L1 and Ml0. So we have this product, and this is just a volume measure. Okay, this is just a volume measure. So we really have to look at the parity of this function. We don't include the parity of this function in determining whether the integral vanishes or not. Which means that if I have some integral over an area dA, and I have some function here f of theta and phi. Okay, this is the kind of integral that I am talking about. So if this function is even, then this integral will be non-zero. If this function is odd over the entire surface of the sphere, we're talking about the sphere here, right? If this function is odd, then over the entire sphere, that when you integrate over theta and phi with the proper area measure, you will get 0. So what we have here, ठीक है, इसको आप यूं भी देख सकते हैं. If you want to integrate over entire space, you have dv, you have f r theta phi. Now the functional dependence on the radius is always even, so you don't have to take that into account. So here what we have, instead of dv, we have sine theta d theta d phi. Okay, and we are looking at the parity of this function. If this function is even, then the integral will be non-zero. If this function is odd, over the entire space over which we are integrating, then the function integral will be non-zero. So let's look at the parity of this function. This is odd, isn't it? Cosine theta, this is an odd function of theta. ठीक है, अगर आप z orbital देखें, टॉप लोब में पॉजिटिव है, यहाँ नेगेटिव. तो दिस इज एन ऑड फंक्शन. इसकी पैरिटी क्या है? -1 raised to power 1, which is -1. इसकी पैरिटी क्या है? -1 raised to power l. ओके,
cos साइन जो होगा वो ऑड होगा. सर उसको ग्राफ बना लेना -π से π.
ठीक है. This is देखो बात ये है, इवन और ऑड क्या मतलब है?
-π से अगर पाए हम उनको ड्रॉ करते थे तो
इवन और ऑड का मतलब ये है. पैरिटी ऑपरेटर क्या है? पैरिटी ऑपरेटर ये है, यू टेक एनी पॉइंट, ठीक है, you take its mirror image about the origin. So you have this point, take its mirror image about the origin, you get here. Now the function is positive here and the function is negative there. So just saying that cosine theta is an even function does not really matter here. Because what your definition of an even function is that if I take theta to be in the, if this theta is negative, but we're not talking about theta is being negative. We are making a transition from theta to pi minus theta, and phi also changes from phi to phi plus 2 pi. So this theta is being replaced by pi minus phi. This is what the parity operator is doing. And what is cosine of pi minus phi? Pi minus theta, sorry. Cosine pi into cosine theta. Now what is cosine pi? -1. So this is minus cosine theta. So cosine theta is an odd function with respect to the parity operator. And we're talking about parity operations. ये बात, ये वो conventional सोच नहीं थी कि ये even function है. So this is an odd function. The parity of any spherical harmonic function is determined by the term -1 raised to power l. ठीक है, तो यहाँ पे L1 है, तो ये माइनस है, ये नेगेटिव टर्म. This is an odd parity function. The parity of this function is -1 raised to power l. Okay. Now suppose l is even. If l is even, this is odd. ठीक है, ये odd है, ये भी odd है. ठीक है, you get an even function. ऐसे ही है.
So
ऐसे वाले.
multiply कर रहे हैं मतलब odd to do function.
Sorry.
We determine the overall हम देखना है कि ये दोनों की overall odd या even है, we are just looking at the product.
Just look at the product, right?
तो odd होगा अगर दोनों odd हो.
अच्छा ये देखो. I will get a term if I take this integral. What is my result? It's proportional to the canonical delta function L1. Okay, canonical delta function ML0. ठीक है ना? अच्छा. Now, when is this integral 0? When is this integral? This integral will be 0 whenever ml is not equal to 0.
This integral will be 0 and ml is not equal to
Yes.
0.
If ml is not equal to 0, this will be 0. For this integral to be non-zero, what do we need to have? We need to have ml equals 0 and l equals 1. Only under this condition will this integral be non-zero. ठीक है, ये बात समझ आएगी. Even और odd parity को भी हम भूल जाते हैं.
Sorry, how did you replace y with delta?
Because for spherical harmonic function they are orthogonal function and we have the relationship sin theta y l m l complex conjugate function of theta phi y l dash m l dash function of theta phi integrated over theta and phi gives us delta l l dash delta m l dash. Okay, because these are orthogonal functions. Spherical harmonic function की property आपने बहुत से सवालों में भी देखी होगी. So this function on a whole will be equal to this, and this will be non-zero only when l equals 1 and ml equals 0. So if I would like to find the probability of making a transition to this state, this probability will be non-zero only when L is 1 and ML is 0, which means that I can make a transition only to NP states with ML equals 0. Which means I can only make transitions to NP states with ML equals 0. So if I have a hydrogen atom that is in the 1s orbital, I put in radiation, and if I am talking about electric dipole transitions, I can only make transitions to 2pz state. Okay? And if my electromagnetic radiation is polarized along the z-axis, this is my condition because that is my initial electric field that I am applying. Okay, I can also make a transition to 3p and the state which has ml equals 0. That state is probably it's 3pz, right? I can make a transition to 4pz, etc. I cannot make a transition to the d orbital or the f orbital, or I cannot make a transition from an s to s, because for that delta L, the change in L is 0. So this electric dipole transition gives us angular momentum selection tools. That's why if I have an electron, such as in the helium atom, which is in the state 2s state, it cannot make an electric dipole transition to the 1s state. So it will remain stuck there for practically forever if we just talking about electric dipole transition. That's why it's called a metastable state. And that is the metastable state that is used in the helium neon laser. Okay, so these electric dipole transitions also give you the angular momentum selection rules, which transitions are possible and which transitions are impossible, considering only first order perturbation theory. Transitions do happen. So you have an electron in the 2s state, it will eventually come down to the 1s state because we are ignoring the higher order perturbation terms and we are ignoring magnetic dipole transitions as well, or electric quadrupole transitions. There are other kinds of transitions as well. Alright, so this gives you an example of what happens when an atom is placed inside an electric field. Now, I would like to keep this formula and try to generalize this a little bit more. That we're inputting monochromatic radiation. Remember that if we start off in the state P2, in the state catch 2, the probability of making a transition to state 1, when you input a radiation of frequency omega is going to be the same. This is the first problem in your exercise in chapter number 14 or 15, whatever it is. What does this mean? This means that if I have cat 2 and cat 1, and initially this state is populated, and I input a radiation of frequency omega, then the probability of making a transition to cat 1, which is the probability 2 to 1 as a function of time, is going to be exactly identical to this. There's really no difference in the physics here. Isn't it so? Physics जिस तरह हमने derive किया है, कोई difference नहीं किया. यहाँ पे आप शुरू कर दें. इसमें different initial condition है कि C2 at time 0 is 1 and C1 at time 0 is 0. So what difference does it make?
इसमें जीरो का
कौन सा?
Z का कॉन्सेप्ट और जो हम रहे थे.
Z का क्या? Electromagnetic wave जो है ये polarized along the Z axis. तो Z polarized wave तो उसी तरह. सब कुछ बिल्कुल एक सा है. So you get the same probability of making the transition to the lower state. So this is what this means is that if you're in the excited state, you input radiation, there's a certain probability of making a transition to the lower state. So this is called stimulated emission. So this is how stimulated emission comes about. It's used in lasers. किस्सा मुख्तसर मैं कहना ये चाह रहा हूँ कि आपकी जो इनकमिंग रेडिएशन अभी तो अज्यूम कर रहे हैं कि ये मोनोक्रोमैटिक है if frequency omega, लेकिन इस तरह की रेडिएशन तो आप कभी प्रोड्यूस कर ही नहीं सकते, अनसर्टेनिटी प्रिंसिपल अलाउ नहीं करता. So what you really have, if you look at the spectrum of your light that is being shown onto the atom, omega goes from 0 to infinity, and you can have a spread of frequencies. A good monochromatic laser, long coherence length, will have a peak centered at some omega. But in general, if you can have broadband sources such as sunlight, you will have a spectrum. Okay. And there is energy in a certain region of omega. Okay. So if this is a plot of u omega is the amount of energy per unit frequency. This is called the spectral density, u omega. Per unit volume, by the way, as well. So this is the energy per unit volume per frequency. It's called the spectral density. So the total energy in the system will be equal to u omega d omega, where omega goes from 0 to infinity. This is the total energy of light. Okay. Now this u omega is called the spectral density. Now we know from basic electromagnetics is that the total energy captured in an electric field per unit volume, the total energy is half epsilon naught, talking about vacuum suppose, into the electric field modulus, right? This is the total energy, which means that I can replace this E naught squared by capital U. Capital U is the total energy per unit volume inside the system. Okay. So this probability of making transition from 1 to 2 really becomes dz transition matrix element square. This electric dipole transition matrix element. E modulus squared is replaced by 2u over epsilon naught 4h bar squared small t squared sinc squared omega minus omega naught e by 2. Okay. Now I can replace this total energy per unit volume by a u omega d omega and integrate over all of space. Now this is assuming that all the frequency, this is still assuming monochromatic light. So if I have a broadband source, that is I have a spectrum that looks like this, in which different frequencies are present. So I can replace this probability by the following: dz matrix element squared t squared 2 epsilon naught h squared u omega small u omega d omega sinc squared omega minus omega naught t by 2 integrated from 0 to infinity. ठीक है ना? ठीक, ये बात समझ आ रही? ये जो टोटल एनर्जी है, अब टोटल एनर्जी मुख्तलिफ फ्रीक्वेंसीज में अगर बटी हुई है, तो इंस्टेड ऑफ राइटिंग कैपिटल Q, your broadband shows you different frequencies, okay, for each omega, using the linearity principle of the Fourier transform, for each omega you have a small u. So you replace this u by a small u, but you have an omega term here, so you multiply it. So this is the weight, this is the amount of the sinc function that you need to have at a particular omega, and then you integrate it over all the frequencies, you get the total. So this thing here is the same as this thing.
ये समझ आ गया, जो ग्राफ है यू ओमेगा का,
ये वाला यू ओमेगा। देखो कोई भी आपके पास लाइट सोर्स है, उसमें बहुत सी फ्रीक्वेंसीज हो सकती है। अगर आप सोलर स्पेक्ट्रम को देखें, उसमें फ्रीक्वेंसीज एक फ्रीक्वेंसी में बहुत सी फ्रीक्वेंसी, लेजर है, किसी अच्छी से अच्छी लेजर, महंगी से महंगी लेजर को भी देखें, उसमें फ्रीक्वेंसी स्पेक्ट्रम है, ठीक है। मोनोक्रोमैटिक, प्योरली मोनोक्रोमैटिक लाइट प्रोड्यूस नहीं करना, ऐसी लाइट प्रोड्यूस करने के लिए आपको इन्फिनिट टाइम चाहिए। अगर आपने ऐसी लाइट प्रोड्यूस करनी है जिसका बहुत कम स्पेक्ट्रम है, तो उसको प्रोड्यूस करने के लिए आपको इन्फिनिट टाइम चाहिए, वो नहीं आप कर सकते, ठीक है, क्योंकि फाइनाइट लाइफ टाइम है हर स्टेट। अब एक्साइट, अगर मॉडर्न फिजिक्स की क्लास याद हो, एक्साइटेड स्टेट की इन्फिनिट लाइफ टाइम होगी, उतनी ही नैरो फ्रीक्वेंसीज आप जनरेट कर सकते हैं। नाउ दिस इज व्हाट हैपेंस इफ यू हैव अ ब्रॉडबैंड सोर्स ऑफ लाइट दैट इज शाइनिंग अपॉन एन एटम, टू लेवल सिस्टम, or not even a two level system, you just taking two levels out of the atom, and this is the transition matrix element between those two levels, ठीक है ना? अब ये आपके पास u ओमेगा का फंक्शन है, ठीक है, spread of frequencies, but this sinc function is tightly peaked at some omega naught, which is the resonance frequency. So this, अब इस u ओमेगा के ऊपर अगर मैं sinc function बनाऊं, sinc squared function, इस तरह का होगा, ये लोब्स ना होने के बराबर है, क्योंकि इसमें एरिया बहुत कम है। तो बुनियादी तौर पर अगर आप इन दोनों फंक्शंस को मल्टीप्लाई करें ना यहाँ पे, तो जब आप इन फंक्शंस को मल्टीप्लाई कर रहे हैं, तो every you get only the value of u that is near the resonance frequency. Everywhere else the product goes to 0. So if this is a tightly peaked spectrum, which means that is omega is really close to omega naught, that is you in the near resonance or on resonance condition, then you can replace this probability by the following: dz squared t squared 2 epsilon naught h bar squared। क्या करूँगा बताओ?
इसके
लिमिट्स तो बाद में भी हम चेंज करते हैं। इस u ओमेगा की जगह क्या लिखूँ? यहाँ पे u की क्या वैल्यू है? फ्रीक्वेंसी क्या है? ओमेगा नॉट, u एट ओमेगा नॉट, ठीक है, u at ओमेगा नॉट, ये कांस्टेंट है, ये इंटीग्रल के बाद आ जाएगा।
u की डिपेंडेंस ऑन ओमेगा क्या है?
कुछ भी हो सकती है u ऑफ सम ओमेगा, लेकिन यहाँ पर u at ओमेगा नॉट है, ठीक है। तो जब ये हुआ, ये 0 से इंफिनिटी डी ओमेगा सिंक स्क्वायर ओमेगा माइनस ओमेगा नॉट बाई 2, है ना जी। अब देखो, दिस इज अ टाइटली पीक्ड फंक्शन, सिंक स्क्वायर इज अ टाइटली पीक्ड फंक्शन, is non-zero only in the proximity of omega close to omega naught. Okay, so it doesn't matter what happens when you have omega far away from omega naught. So I can replace these limits by minus infinity to plus infinity, because everywhere else the function is zero, close to zero. Okay, now this is a standard integral that you can find or you can calculate. It's quite easy. Okay, this gives you 2 pi over small t. ठीक है, so the probability of making a transition from 1 to 2 with a broadband source equals dz squared electric field, अच्छा t squared 2 epsilon naught h bar squared u omega naught 2 pi over t, ये इस इंटीग्रल का ये रिजल्ट है, ठीक है। सो हल कर रहे हैं, p1 to 2 equals approximately dz modulus squared, ठीक है, ये 2 से कटा है, ये क्या है, 2 से कटा, पाई है, पाई u ओमेगा नॉट स्मॉल t 2 कट गया एप्सिलॉन नॉट 8%. This is the probability of making a transition from state 1 to 2 when you shine a broadband light source. Okay, and you have to take into account the spectral density at the resonance of the light at the resonant frequency corresponding to the pitch. ठीक है, and this probability is a linear function of time. ठीक है ना, so अगर आप प्लॉट करें इस probability को as a function of time, goes like this. So with time this probability keeps on increasing. You're shining broadband light on a light source. The probability of that this system has made a transition to the higher state is going to increase with time. But then there are additional problems when once this state is exciting, you have light coming in, the probability of making a downward transition also goes up. Okay. अब लेजर्स का जब हम देखेंगे, शायद हम देख पाएंगे अगले लेक्चर में, तो ये इफेक्ट है। फिर यहाँ पे एक स्पॉन्टेनियस एमिशन की भी एक प्रॉब्लम है कि लाइट के बगैर उसमें टू डाउन बना सकते हैं, ठीक है। बहरहाल, और also remember that this probability, this linear relation is only valid when the probabilities remain small, because that is our limitation for discussing the perturbation theory.
So उसके लिए टाइम पीरियड बहुत स्मॉल रखना पड़ेगा,
स्मॉल टाइम के लिए ये वैलिड होगा, तभी
ये अप्रोक्सीमेट रेंज कितनी होगी टाइम?
I mean, it all depends upon the magnitude of this. It all depends upon the magnitude of this. अच्छा, दूसरा बार आप ये देखें, anyone else has a class? रुक सकते हैं,
वो तो रुक जाएगा,
रुक देना, वीडियो देखें,
सर कितना टाइम हो गया?
मेरे ख्याल में आधा मिनट,
सर आपने कहा था
बस अब एक फ्लो है,
2 मिनट में मैम शुरू हो रहा है,
थोड़ा चलना क्या क्लास जरूरी है।
ला
आप जाएं फिर ये वीडियो देखें, नहीं आप मेरी वजह से आप लैब अच्छा आधे घंटे के अंदर कोशिश करता हूँ कि मैं फोटोइलेक्ट्रिक इफेक्ट दिखाना चाहता हूँ बस। probability of making a transition in the presence of broadband light source from 1 to 2. Now if I would like to find out the rate at which transitions are made from 1 to 2, you're shining light, you want to find the transitions per unit time. This will just be the derivative of this. So this rate of going from 1 to 2 equals dz modulus squared by u omega naught, u at omega naught epsilon naught h bar squared. This is independent of time. So the rate is independent of time. So with the slope of this line is the rate. This is called the Fermi's golden rule. That is, the probabilities of making transitions are independent of time.
per second के हिसाब से होगा।
Per second के हिसाब से। अच्छा देखो, dz हमने इसलिए लिया क्योंकि initially the light that is polarized is along the z axis. अगर वो x किलोमीटर तो dx लेंगे, y किलोमीटर तो y लेंगे। ठीक है। दूसरी बात आप एक और नोट करें कि light is being treated as a classical radiation, right? It's not quantized. So this light is polarized along the z axis. This is z axis. The electric dipole operator can be pointing in an arbitrary direction. ठीक है? The d operator, the d vector, right, can be pointing in an arbitrary direction. So what we really need to take into account, this term is just the dot product of d with the electric field, modulus squared, right? So inside the modulus squared we have this, with of course a minus sign as well. Okay. Now this is always polarized along the z-axis. So this term is really minus d operator E naught, right, along some direction, minus d, the length of the dipole operator. So you have a molecule or this is just the length of a vector. It's E times ER. ठीक है, R ये आपकी expectation value हो सकती है particular orbital. So this is the length of this dipole operator E naught into cosine of some theta, right, which is the angle between the electric field and the dipole vector, and of course the cosine omega t as well. है ना, ऐसा ही है ना. अब देखो, this means now if I have a gas like hydrogen in which the dipole operators are pointing randomly in all directions. Okay. This means that theta is random, totally random. This is the magnitude of d, not dz. This d cosine theta is dz. अगर इसको देखो, if I have a distribution of dipole operators, I would really like to find the d dotted with E average value, right? The average value of this. Okay, this is what I need to find. Now this means that I really need to find, if I take the modulus squared, this becomes d squared, this becomes epsilon naught squared. So I need to find the absolute value of cosine squared theta. Okay. So the average value of cosine squared theta is something that I need to determine. Because what my purpose is, I would like to replace this dz by d. D is more natural. That is independent of the coordinate. Okay. And it, ठीक है, मैं dz को d से replace करना चाहता हूँ, क्योंकि अगर एक different atom होगा उसका dz different होगा, क्योंकि it's pointing, its dipole operator is pointing in a different direction. So my goal is to replace dz by d. but I have to take into account this orientational averaging. I have to average over all the possible orientation of the different dipoles in the system. Okay? So which really means that I need to find the average of cosine square theta. So the average of cosine square theta क्या होगा? Cosine square theta इसको proper element के साथ यानी sin theta के साथ multiply करके d theta d phi, ठीक है? Theta goes from 0 to pi, phi goes from 0 to 2 pi, and I have to normalize this as well, which means I have to find in the denominator sin theta d theta d phi. ऐसे ही करेंगे ना इसका average, ठीक है? So this turns out to be equal to 1/3. किसी भी number की average, you have to take the integral with the probability density function over a sphere. There is ये area element है ना on the sphere, that is sin theta d theta d phi, ठीक है? और इसको फिर normalize कर दिया आपने, पूरे area से divide कर दिया.
So function को integrate कर रहा हूँ over the area.
मुझे एक बात तो, if you want to find the function of f, the average of f, कैसे करेंगे? dA f over the area, ऐसे करेंगे. That's what I mean. ओके, आपको जब आपने over the area किसी भी एरिया इंटीग्रेट करना है, you have to use the proper area element, surface area element, ठीक है? ये 1/3 आ रहा है. So this means I can replace this dz squared. This dz squared in the formula can be replaced by d squared over 3. ठीक है ना? This means that the rate is given by d squared transition matrix element squared pi u omega naught 3 epsilon naught h bar squared. So if I have many atoms placed inside a broadband light source, the rate of making transitions from 1 to 2 is proportional to the square root of the matrix element that is connecting those transitions, the spectral density at the resonant frequency corresponding to the transition, and it's independent of time. This is just the Fermi boson. Okay. Now one more example, the photoelectric effect. I would like to explain the photoelectric effect based upon all of this theory. I can also explain lasers, but I think you've already seen lasers in modern physics and probably different contexts. I would like to describe the photoelectric effect. Remember, Einstein got the Nobel Prize in physics due to Brownian his description of the Brownian motion and the photoelectric effect. He quantized light and used the photoelectric effect to describe that light has to be quantized. It has to comprise of photons. But what we now know, and what this description is going to show you, that the photoelectric effect can be described without taking into account the photon picture of light. It does not show the quantization of light, because you can describe the photoelectric effect just by classical electromagnetic radiation falling upon a quantized system. So the atom has to be quantized, but the light need not be quantized. So you can use the semi-classical description, as it is called, to describe the photoelectric effect. अभी तक हमने लाइट को कोई क्वांटाइज तो नहीं किया कि फोटॉन्स निकल रहे हैं आज. इट्स जस्ट अ क्लासिकल इलेक्ट्रोमैग्नेटिक वेव जिसकी एनर्जी डेंसिटी स्पेक्ट्रल डेंसिटी की है, डिपेंड्स अपॉन इलेक्ट्रिक फील्ड. दिस इज एन एम्पलीट्यूड स्क्वायर. दिस इज अ क्लासिकल क्वांटिटी. नाउ व्हाट इज द फोटोइलेक्ट्रिक इफेक्ट? इन ऑर्डर टू अंडरस्टैंड द फोटोइलेक्ट्रिक इफेक्ट वी विल हैव टू मेक अ डायग्राम. ओके, डायग्राम क्या है? होता ये है कि एक इलेक्ट्रॉन है किसी एनर्जी लेवल E1 में, ये वैक्यूम है, इसकी एनर्जी हम कहते हैं 0 है. ठीक है, so the electron is lying inside the metal at some energy level E1. So this could be the conduction matter. ठीक है, and this could be the work function. Okay, or okay. So let's call this the ionization energy, EI. So electron is inside some level. It's not at the vacuum level. Above the vacuum level, the electron is free. So this is a continuum of energy level. For a free electron, we know that the energy is not quantized. Quantum 1 में आपने पढ़ा. So here we have a continuum of levels. The energy can be continuous. So instead of having quantized levels, continuum of levels, I can make closely spaced energy levels. Okay, just for modeling purposes. So the closely spaced levels, it's really a continuum of levels. Suppose light of a certain frequency comes in. And I would like to make a transition from this initial energy level to this final energy E. This is my final energy E. यहाँ पे energy 0 है. ये energy कितनी होगी? Minus EI. Alright? So this is 0. This is the vacuum level when the electron has become free from the atom. This inner level is E1, which is minus the ionization level. Okay. And the energy of the emitted electron, the photoelectron that has been ejected from the metal, is capital E. I want to find this probability of making a transition. And my incoming light has a frequency omega, some omega. Okay. And E minus E1 is the difference between this energy level and between the initial and the final, is E plus E capital I is H bar omega naught. The resonant frequency, and the incoming light has frequency H bar omega. ये है system की definition. I would like to find the probability of making this transition. Initially I am here. So there is light coming in with a certain frequency omega that's close to omega naught. Omega naught is the frequency difference between the initial and the final states. ये energy 0 है, ये energy capital E, ये energy है minus E sub I. हाँ जी मैम. ये E है. ये 0 है.
The difference of the frequencies of E and E1.
Initial and final. ये सिस्टम की प्रॉपर्टी है और इनकमिंग लाइट ऑफ फ्रीक्वेंसी ओमेगा थी. ठीक है ना. अब I can use the same formula as I've written here. This one. The probability of making the transition is of course this multiplied by t. This probability of going from E1 to capital E, of going from E1 to capital E is d squared by u of omega naught, right? Epsilon naught h bar square into time. और साथ साथ सिंक फंक्शन और ये तो रेट है. यहाँ पे सिंक फंक्शन सिंक स्क्वायर. ठीक है. बिल फर्स्ट में मोनोक्रोमेटिक लाइट सोर्स में. ठीक है. मैं ब्रॉडबैंड लाइट सोर्स में है. So instead of u omega, what do I have? I have this formula. ये वाला. ठीक है. जहाँ जहाँ dz स्क्वायर है मैंने इसको d स्क्वायर और 3 से रिप्लेस किया. एप्सिलॉन नॉट स्क्वायर स्क्वायर 3. This is my probability, right? dz square epsilon E squared, T squared, sin square omega minus omega naught E by monochromatically. Okay. Suppose I'm showing monochromatically. Okay. So I have D square over 3. I have E naught squared. I have 4H bar squared. I have T squared. And then I have sin squared omega. What is omega now? This is my incoming rate. Omega minus omega naught. Now what is my omega naught? Remember that my H bar omega naught is this E plus EI, right? So instead of omega naught, I can write E plus E sub I over H bar into T over 2. Right? So this is my probability of making the transition. ठीक है, मैं जरा यहाँ पे जाता हूँ, मैं भी जरा आसानी से सीखूँ. अभी बड़े ध्यान से, सिर्फ 10 मिनट का आर्गुमेंट रह गया है. इससे सारा सारा नोबेल प्राइज इसमें आ जाएगा. फोटोइलेक्ट्रिक इफेक्ट. ये वाला फॉर्मूला ठीक है ना? Alright. So this probability, I can write this probability as E square 12H bar square E naught squared, electric field squared, sin squared मैं खुद से इसको H bar ओमेगा लिखता हूँ. यानी I multiply this parenthesis by H bar, I get sin square H bar omega minus E minus EI, right, multiplied by 2 over 2H bar. ठीक है. Now this is and this sin square is sine square of something, and it's a square. So if this argument goes to negative, it doesn't change the result. So what I would like to do now, in the next step, I would like to write this in the following form: D squared E naught squared 12 H bar squared sin squared capital E minus H bar omega, right? Minus H bar omega plus EI. But I can write all of this in this form into 2 over 2H bar. Actually, it's a come this. Go ahead, speak.
Sir, even though the negative type,
देखो, sin squared of theta equals sin squared of minus theta. So this is the probability of making a transition from this initial energy level to this final energy level. ठीक है? अब ये E is a continuous variable. I would like to make my E a continuous variable. ठीक है? और notice करो कि ये जो term है H bar omega minus EI. This H bar omega minus EI is how above am I from the vacuum level. which is the kinetic energy of the photoelectron. Because in this case, when the electron has been ejected, it does not have any potential. It's a free electron. So all of its energy is kinetic energy. So this is just the energy of the emitted electron. So by looking at the energy of the emitted electron, the photoelectron, I can tell what is the EI. I can tell how far from inside the metal or inside the atom is the electron coming from. This is the principle of X-ray photoelectron spectroscopy, by the way. Now anyway, ये मैथमेटिक्स समझ आ गया और डिफरेंट टर्म्स आपको समझ आ गए, ठीक है. अब आई वुड लाइक टू कैलकुलेट द टोटल प्रोबेबिलिटी एज अ
ये ई जो है ये भी जो है टी ओवर एच बार से
सारा
मल्टीप्लाई होगा.
अच्छा, अब आई वुड लाइक टू फाइंड आउट द टोटल प्रोबेबिलिटी ऑफ ejecting an electron. Oh, यहाँ पे t square भी. ठीक है. I want to find the total probability that a photoelectron is emitted. The probability of emission of an electron by an incoming radiation of frequency omega. ठीक है. अब इसमें दो तीन बातें देखें. My variable. Now, electrons can be ejected with any frequency ranging from 0 to infinity. So E, capital E, has become my variable of interest. I would like to integrate over this energy variable. ठीक है, different electrons, different energy से emit होंगे. The total probability is the final state could be this state, could be this state, could be this state. Right? Different photoelectrons will have different final energies, even when the incoming radiation of the frequency omega. So I would like to find the total probability. So my capital E becomes a variable of interest from 0 to infinity. However, notice that this is a function of energy. Alright, so this goes inside the integral. This term D depends upon what is the dipole operator. The dipole operator is minus E times R. Okay, now this is general definition of electric dipole operator. Now R is the distance of the electron from inside the dipole. We're talking about electric dipole transition. So now we have a quantum state here, which in general is at a different distance, different effective R from its initial position. So, okay, and you change the energy of the outgoing electron, this dipole operator is going to change. So this D is also a function of the energy of the ejected electron. Okay. So I can replace all of these terms. I can find the total probability in the following form: E squared 12h bar squared T squared energy E going from 0 to infinity dE, right? Small d, which is a function of E, modulus squared sec squared E minus h bar omega minus EI, all of this being multiplied T over 2h bar. Okay, but an additional factor has to be included. Now these are continuum energy levels. Okay, now the point is, per unit energy, how many energy levels exist? If in a certain range of energy there are more levels, then there is a higher probability of making a transition to that energy band. ठीक है, जितने अगर एक ही एनर्जी पे बहुत सी स्टेट्स एग्जिस्ट करती हैं, so there is a higher probability of making transition to those states, because each one of them contributes a probability and all the probabilities will add up. So what I really need to include here is a factor that tells me how many energy levels do I have in the continuum state per unit energy. So I put in a factor here which is called the density of states, GE, which is a function of energy. And for different kinds of systems, this GE is different. ये जो लोग तफसीलात में क्वांटम मैकेनिक्स की जाते हैं, सॉलिड स्टेट फिजिक्स पढ़ते हैं, या मैं आपको मिसाल दे रहा हूँ. रोटेशनल एनर्जी लेवल्स हैं L equals 0 है, ML की एक ही पॉसिबिलिटी है 0, L equals 1 है, ML की 3 पॉसिबिलिटीज है 1, 0, -1. तो टोटल एनर्जी निकालनी हो सिस्टम की in E equals L equals 1 state. So you will have this state populated, this state populated, this state populated. You will have a density of 3 as compared to this. Now I have to include this density of states factor here. Just tell me how many energy levels do I have at a particular energy E. ठीक है ना? It does make complete sense. Now this is my formula. Okay. Now if you look at this formula, the first thing that you observe, okay, इसकी observation हम बाद में देखते हैं. Now this is a tightly peaked function. If I draw this function, E is my variable of interest, and I want to draw this function, all of this on this energy axis, where will it peak? It will peak when E equals this factor. So it will peak here, h bar omega minus E capital I. यहाँ पे इसकी peak होगी. है ना? And if h bar omega minus E I, h bar omega minus ei, this is omega now, okay? Ab, if this energy, which means that this function is tightly peaked at this value, everywhere else the function rapidly decays to 0. So for energy values that are close to this, this function is tightly peaked, okay, and everywhere else it is almost equal to 0. So I can replace this by approximately E naught squared T squared 12 h bar squared. ठीक है? Now this is the density of states at this particular value of energy, because everywhere else it's 0. So I can take this outside the inductor and I can find the density of states at h bar omega minus ei. This is just the density of states. Now if this is my incoming radiation of frequency omega, I just need to find the density of states here. I don't have to take into account the density of states elsewhere. Just find the density of states here. I put in a different omega, different radiation, just find out the density of states at the value which corresponds to the frequency omega. So I just need to take into account the density of states here. I don't take into account the density of states elsewhere, even though I'm calculating the probability over the entire continuum. So d at h bar omega minus ei. Similarly, this becomes d at h bar omega minus ei modulus squared, right? And I can replace, now this is just an integral from 0 to infinity over a sinc function. I can replace this from minus infinity to plus infinity. I will get 2 pi over d. ठीक है, अब इस रिजल्ट बहुत ही अच्छा खूबसूरत सा रिजल्ट है. एप्सिलॉन नॉट टी स्क्वायर का घटा के टी रह जाएगा इसका टी 12 6 h bar squared by g at h bar omega minus ei and b at h bar omega minus ei modulus squared into t. Now this is the total probability that an electron is ejected from the system. Okay, and this probability increases with time. You keep on shining light on a system, the probability of detecting electrons increases. This is what happens in a real photoelectric. Okay, you can also write this as some eta it. T is this time. I is just proportional to the intensity of the electric field, proportional to the modulus squared of the electric field. So instead of E mod square, with certain factors are written the intensity of the incoming radiation. Higher the intensity of the incoming radiation, more photoelectrons will you observe. This is what happens in a photoelectric experiment. It explains your observations. This is just the quantum efficiency of the process. Everything else is the quantum efficiency.
Sir, I's intensity depends on G.
It depends upon G. No, I depends upon E mod square. I is just the intensity of the incoming radiation. Everything else is eta, the quantum efficiency. एक चीज हमें नजर आ रही, probability is increasing linearly with time. The probability of photoelectrons being ejected, which is the photoelectric current in an experiment, increases with the intensity of light. ये भी observation है. और एक ये भी observation हमें कहीं से लानी चाहिए कि if H bar omega, which is the incoming radiation, has an intensity smaller, this energy smaller than EI, no photoelectrons will be ejected. ये भी है ना कि threshold है photoelectric effect के. अब अगर आप ये देखें, ये curve है, ठीक है? This is just this curve, and you're integrating from 0 to infinity. If the peak of this curve somehow lied in this region, then this integral would be 0 and no photoelectrons would be ejected. देखो ये 0 to infinity integrate कर रहे हैं. अगर ये peak होता ये function where at some value which is negative, at some value of energy where it is negative, then no photoelectrons will be ejected. So when will this be negative? When H bar omega is smaller than EI. ये तभी नेगेटिव होगी.
हमें तो लिमिट चेंज करनी थी.
उससे पहले अभी क्या लिमिट्स अभी ना चेंज. देखो इस फंक्शन टाइटली पीक होना है एक वैल्यू ऑफ एनर्जी पे, ठीक है ना? तो उस वैल्यू ऑफ एनर्जी पे G और E को आप इंटीग्रल से बाहर ले लीजिए, फर्क कोई नहीं पड़ेगा. So if H bar omega is less than EI, this integral is going to be 0 and no photoelectrons will be there. And this is what you observe. This is the quantum effect. That if the incoming radiation has a frequency smaller than this, it will not eject any photoelectron, no matter how strong E square is, no matter how strong the intensity of the incoming radiation is. तो photo G.
तो ये हम इसलिए बोलेंगे GE 0 है.
कब?
ये जो है H cut omega is less than EI है, तो GE जो है वो भी 0 नहीं होगा.
ये तो हमें नहीं पता कि क्या है, जो भी हो. Or the photo detection rate at which photoelectrons are coming out is independent of time. ठीक है? The photo current is in other words the rate of ejection of photoelectrons is the photo current. Charges per unit time को चार्ज से मल्टीप्लाई करने वाला इलेक्ट्रॉन you get the photo current. तो ये क्वांटम मैकेनिकल इफेक्ट है, टाइम डिपेंडेंट परटर्बेशन थ्योरी से आ रहा है, पूरा एक कंप्लीट एक्सपेरिमेंटल पिक्चर कंसिस्टेंट. और दिस नोबेल प्राइज विनिंग वर्क does not require the quantization of the electromagnetic field. Just can be described by treating the electromagnetic radiation as classical wave. ठीक है? So for the exam, I would request you. The exam is going to be during the recitation time on Monday. There is no class on Monday morning to prepare for your exam. During the recitation time for 2 hours, there will be an exam.